Assalamu alaikum students. On behalf of the Department of Electrical and Computer Engineering, I, Ali Rahman, welcomes you to our first session covering the topic registers for the course Digital Logic Design. This session is specifically designed for the students of BCS3A and BCS3D. So to start with, let us first see the contents which we will be covering in today's session. First of all, we will be having the review what we have learned in the previous session. Then we're going to introduce the registers. Then we're going to define registers and counters, that are the basic building blocks for the memory modules and as far as those devices in which the timing information is important. Then we're going to discuss our example with the simplest register, how we're going to construct that register. Basically, we will be utilizing that flip-flop concept. Flip-flops are the basic building blocks for the registers as well as for the counters. And then we'll conclude our discussion with the example with the registers having the capability of the parallel load. As far as the reference readings and acknowledgements are concerned, now students, we are reading chapter number 6 of the book Digital Design with Introduction to Verilog STL by Morris Mono. So all the discussion and all the content has been taken from the book, and the slide content is being originally designed by the author itself, so which is basically being modified as per your requirement. So before going to the registers and counters, let us first see what we've studied in the previous session. Our previous session basically focused on the sequential logic design. Before that, we were discussing the combinational logic design. So in the sequential logic design, there is a memory element involved, or we can say a feedback element involved, and output is basically dependent upon the inputs and the previous information or the history that has been stored or that has been saved. So we have discussed the examples of the latches that are the single bit storage devices, that were the level trigger devices, in which we've discussed a variety of latches. For example, the SR latch, the D latch, the gated D latch. Then we'll switch to the flip flops, that are the clock sequential devices. Basically, those devices were synchronized with some edges of the clock, and synchronization was achieved with some clock source. And then we've discussed the examples of D flip-flop and JK flip-flop and D flip-flop. And the most important thing which we've seen, that in those flip-flops there is no indeterminate state or undefined state. And there is one very important state which is being used in counters where we were discussing the counters, that is the toggle state. So that state is being utilized in the counters. So we're going to discuss that stuff in detail when we will be discussing counters in detail. So that was our discussion in the previous session. Now we'll switch to the registers and counters. Registers are basically the storage devices, the multiple bit storage devices. We can say that these are basically the set of flip-flops, a connection of flip-flops, and the flip-flops are dependent upon the number of bits we are going to store in that particular scenario. So that particular setup do contain the set of flip-flops. So we've got a set of flip-flops. It can be a D flip-flop, it can be a JK flip-flop that is used to store some binary bits, and with the possibility of some additional gates in order to perform data processing tasks. This thing we will be clearing when we will be discussing the registers to the parallel load. Well, in that particular session we are having some additional combinational logic components or combinational gates that allows us the possibility to process data. So in that particular scenario, we can have some additional gates with a set of flip-flops. So what are the basic purpose of the registers? To store basic information, to store the binary information. We can store data, we can store binary information in the digital system, and we can manipulate information as well by using the registers. So registers are basically utilizing the flip-flops, and flip-flops are the basic building modules in order to store some data. So there are various applications of the registers. We will be discussing that applications in detail when we will be discussing the shift registers as well. So In order to define the registers, basically these are the components that has the set of flip-flops and some additional gates to perform some data processing tasks. Now let us discuss the counters. Counters are basically the examples of the register itself. So we can say that counter is also a register. So what is the difference between a register and a counter is the way of processing basically the counters have. Basically the registers, we can say that counters are the registers that goes through some predetermined sequence of states. So in those applications in which it is required to have some predetermined sequence of states, or to have some count information, or to maintain some timing information, or the behavior of the device changes with occurrence of some clock event with some sequence of states, that is basically a counter. As far as its name is concerned, the device that has the capability to count something. So that count sequence is basically dependent upon the structure of the implementation of that particular counter and the resources that are being utilized in while implementing the counter. So we can say that it's a special type of register. So in order to distinguish between a counter and the register, basically it's a special type of register that has some predetermined sequence of states, while the normal registers don't have some predetermined sequence of states. Now where we use that counters basically are those sort of circuits are employed in those scenarios in which the sequence and control of operation is required. For example, we can say that in processor, when we are processing the list of instructions in order to execute the instruction cycle, we can say that a counter is required that has the capability, or you can say that that this counter is called, sometimes called the instruction counter or the program counter in that particular scenario, that helps us in maintaining the sequence of instructions so that the processor can process those instructions in a particular sequence. So that is a one prime example of the counter. Another example of the counter, we can say that in the traffic light signals which have the capability of the to have the timing information, we can utilize the counters circuits there as well in order to maintain some timing information, or to count some sequence. For example, the traffic light signals are operating on some timing information, and that timing information is dependent upon the clock source, and some after the transition from one state to another state, that is dependent upon the time that is being processed in that particular state. So we can use counters there as well in order to maintain the sequence. So to conclude with, the registers and counters a bit alike same, but the counters are the special type of registers that have some predetermined sequence of states, while that is not the case while we are discussing the registers, the simple registers. So let us see the simplest register that we can implement. Basically, if we see that in this particular scenario, let me change the pointer. In this particular scenario, in which the block diagram is being represented and a symbolic representation is also been provided, we are using the set of flip-flops. In that particular case, we are using 4 D flip-flops. That means that this register has the capability to process 4 bits. First thing. Secondly, we can say that while looking at the structure, all the registers are connected with a common clock source. See, the clock source that is being applied on this register is common, this line. And that signal is named as clock. Second important observation is, in order to clear those flip-flops or to reset those flip-flops, we are using a signal that is being named clear. and these flip-flops are active low reset flip-flop, which means that whenever there is a value of 0 on this clear line, those flip-flops which are connected with this clear line are reset to their default value. Now if you see the symbolic representation, we've got 4 inputs that are being labeled as D0, D1, D2, D3, and in this logic diagram we've got 4 inputs, I0, I1, I2 and I3. Basically these are the 4 inputs that are being connected with these lines. So this is basically I0, this is I0, this is I1, this is I2, and the last one is I3. These are the setup inputs, the 4-bit inputs that are being parallel applied at the same time on the flip-flops. And we've got the 4 outputs Q0, Q1, Q2 and Q3, which are labeled in the block diagram or in the representation as A0, A1, A2 and A3. So Q0, this is basically A0, this is A1, this is A2 and this is A3. This clear line is basically which is connected with the reset input of all those flip-flops, is used to reset or the clear all the outputs of those respected flip-flops that are being connected with this clear line, and this is basically the clock source. So this is the clock source. Basically this symbol represents these 4 flip-flops in this particular scenario. So this register has the capability to process 4 bits at the same time. So we applied the inputs on the respected lines I0, I1, I2 and I3. Whenever there is a leading edge of a clock, because these are the positive edge triggered D flip-flops, the inputs are assigned at the output. So A0 is assigned as I0, A1 is assigned as I1, A2 is assigned as I2 and A3 is assigned as I3. So output is basically equals to the input, and these input bits are basically stored at the respected outputs of those flip-flops. So in that particular case, whenever there is a leading edge or the rising edge of the clock, the data A0, A1, A2 and A3 are updated. So if at any time instant, if we have to reset our flip-flops, what we have to do is we have to set this clear line equals to 0. What we have to do is we have to set this clear line equals to 0. So this 0 is applied on this reset as well as on this reset as well as on this reset and as well as on this reset, and all those 4 D flip-flops are reset to their default value. So A0 is flushed, A1 is flushed, A2 is flushed and A3 is flushed to logic 0. So basically this clear input is very much useful for cleaning the registers to all 0 prior to its clock operation. So whenever there is a requirement to clear those registers, what we have to set is we have to set this control line, we can say that, or the clear line equals to 0. So in a normal mode of operation we have to set this line equals to 1. So by default this line should be equals to 1. We have to set this clear line equals to 1 for normal operation. So students, this is basically a 4-bit simple register that has the capability to store 4 binary bits. So what if we have to implement a 32-bit register in that particular scenario? How much flip-flops do we need in order to implement or in order to store those 32 bits? And we have clearly said that the number of flip-flops are totally dependent upon the number of bits. So we do need 32 flip-flops. Here in that particular case we are using D flip-flop. We can also use JK flip-flop. We can also use T flip-flop. Can we use T flip-flop in order to store binary bits? No, I don't think so. So either we are using D flip-flop or we are using JK flip-flop in order to store binary information. While we are discussing the counters, then there is the provision that we have to use those flip-flops that can be operated in the toggle state. Now let us discuss a register, a particular example of the register that has the capability to parallel load the data to the outputs. Here we are introducing a control line or a signal whose values specify that whenever we are loading a data into the register or whenever we are holding the register to its no change state. So basically we are introducing this load line. This is basically a signal control signal we are introducing, and we have named it as a load. Whenever its value is 1, in that particular case the data is loaded to the register, and if we set its value to 0, the register should maintain the no change state. Should maintain no change state. So what are the important components in that particular register? Basically it do contain the set of flip-flops, and those set of flip-flops are dependent upon the number of binary bits which we use to store. And then we have a dedicated control line that whose value specifies that whenever we have the capability to load data into the register and whenever we have the capability to hold the register, so that whatsoever the change in the input is not being reflected on the output. So this load is basically the operational line or the major control line that we are introducing, and we will see how we're going to use that line by using some additional combinational gate in order to achieve this functionality. So whenever the load is 1, all the bits of the data inputs are transferred into the register. So this is the transfer state or the loading state, and whatsoever the data we have provided on those input line are parallelly loaded on the output lines. So we are applying the inputs at the same time. We are not following any sequence or the serial operation here. So on the other hand, if the load value is 0, the outputs of the flip-flop are connected to their respective inputs, so that there is a no change state that can be maintained. Now let us see the implementation of that particular register with the parallel load, and we're going to discuss or dry run that diagram one by one in order to discuss all the cases or all the scenarios. Well student, this is the logic diagram, or you can say that a 4-bit register that has the capability with the parallel load. This is basically figure 6.2 of the book. So let us discuss how this setup will work by dry running this setup. But first of all, let us see the resources that are being utilized in this particular scenario. First observation is we are using 4D flip-flops. So one important thing which we can observe from this thing is that this particular register has the capability to hold 4 binary bits. So those outputs are A0, A1, A2 and A3. Whenever A0, A1, A2 and A3 should have the value I0, I1, I2 and I3. These are basically the inputs of our particular system that are being dependent upon the value of this control line, and how this control line will operate we will discuss shortly while discussing that scenario. Second thing, we can say that there are the sequence of gates. For example, two AND gates and an OR gate setup, or a pair that has been connected with the D line or the D input of each flip-flop. Third important thing which we can observe is that this is the positive edge triggered system. And the fourth thing in this particular scenario, that these flip-flops don't have any reset provision. So if we have to provide the reset provision also, then there is additional line on this flip-flop that has been set as reset, that is being connected. All the reset inputs are being connected to a dedicated signal that can have any unique name, for example RST or reset, or in the particular case, in the previous case, we have the name clear. So in this scenario we don't have any sort of reset provision, but we can introduce the reset provision also in this particular scenario. Now how this setup will work, let us dry run this, and let us set the value of this particular line load equals to 0 in first case. Let us set this value equals to 0. So when the and let us assume that whatsoever the value of I0, I1 and I2 is, so for the case of our discussion, let us assume that I0 equals to A, I1 equals to B, B can be anything, it can be 0, it can be 1, I2 equals to C, I3 equals to D. Just to show you that how these particular values are being reflected at the output. So A, B and C, D can have either 0, can have either 1, so that is dependent upon the combination of inputs at that particular time instant that is being applied. So I am just discussing it in general. So we can use either A, B, C, D, or we can use those inputs labels as well as I0, I1, I2 and I2. Let us use the labels that are being already assigned to the input. So I0 can be 0, 1, I1 can be 0, 1, I2 can be 0, 1, I3 can be 0, 1 at any time instant. So I am erasing those A, B and C and D. So we have set this value equals to 0. The value of load equals to 0. Let us see what will happen if we set this value equals to 0. This inverter will make it to 1, and again it's been inverted to make it 0. So let us see this output line that is generated by the second inverter. Let me label it as inverter number 1, and this is inverter number 2. This 0 is applied on the input of this AND gate, at the same time this AND gate, at the same time this AND gate, and at the same time this AND gate, which means that whatsoever the second input of that particular AND gate is, the output of that particular AND gate is permanently switched to 0. In that case, in that case, in that case, and in that case, which means that this AND gate is not contributing at the output, this AND gate is also not contributing, this AND gate is also not contributing, this AND gate is also not contributing, which means that these I0, I1, I2, I3 cannot be moved forward to the D inputs of these flip-flops. Now let us see the second AND gate, or the pair of the second AND gate in that particular pair. This one is moved to this AND gate, to this AND gate as well, to this AND gate as well, and to this AND gate as well, which means that the second input of that AND gate is now the contributing input. And we can see that the second input of this AND gate in this case is A0 in this particular case, A1 in this particular case, A2 in this particular case, and A3 in this particular case. A0, A1, A2 and A3 can have 0, can have value 1. Let me just erase the additional information. Now this is the particular case. So what is forwarded by these AND gates? The output of this AND gate is basically equals to A0. So if A0 equals to 0, this equals to 0. If A0 equals to 1, this equals to 1, which means that A0 is forwarded to this OR gate. In this case A1 is forwarded. In this case A2 is forwarded. And in this case A3 is forwarded, while keeping in mind that the other input of this OR gate is 0. So the output of OR gate is now dependent upon the value of A0, the value of A1, the value of A2 and value of A3. So we can say that the output of this OR gate is A0, this is A1, this is A2 and this is A3. So upon the application of the leading edge of the clock, whatsoever the input at these D lines are shifted to the output. So this Q output is basically equals to A0, A1, A2 and A3, which means that these flip-flops are holding their previous value, so there is a no change state. Now let us see the second scenario when we are setting this load value equals to 1. Let me erase this information first. Now what we are doing is that we are setting this value equals to 1. This inverter inverts it to 0, which is once again inverted to 1. So this 0 is being applied here, here, at this gate, here and at this gate. So automatically the output of these AND gates are 0. Now let us see the status of the other AND gates. Here we are getting 0 here, here we are also getting 0 here, we are also getting 0 here, we are also getting 0 here. So whatsoever the previous output A0, A1, A2 and A3 is, that are not been reflected to the inputs of these D flip-flops. So let us see the second line. Let me highlight it first. This line. That is being connected with this gate, that is being connected with this gate as well, and this gate as well. Now interestingly, the second input of these gates are I0, I1 and I2 and I3. So whatsoever the value of I0, I1 and I2 and I3 is, that is been moved forward by these AND gates. So the output of this AND gate equals to I0. I0 can be 0, I0 can be 1. That is dependent upon whatsoever the value is being applied at that particular timing instant. Here we got I1 in this particular case. Here we got I2 in this particular case. And last but not the least, the last AND gate will contribute I3. Now the output of these OR gates are I0, I1, I2 and I3. Now application on the application of the leading edge of the clock, this I0, I1, I2 and I3 are being stored at the output, are being loaded at the output at the same time parallelly. So A0 is equivalent to I0, A1 should be equal to I1, A2 should be equal to I2 and A3 is equal to I3. So in that particular case, the data that is being provided on the input lines I0, I1, I2 and I3 is being loaded to the output. So students, I hope so. Now the operation of this register is very much clear. Whenever the value of load is set to 0, we are using the no change state. The outputs of this register are being held to the previous value, that is the no change state, with the help of the combinational gates. And whenever we set the value of this load line equals to 1, in that particular case, whenever we have to load the data to the output, we have to set this value to 1. And in that particular scenario, whatsoever the inputs that is in parallel applied on the respected input lines I0, I1, I2 and I3 at the same time, that is being loaded to the output. So outputs are being set to I0, I1 and I2 and I3 in that particular case. So student, this is all for today's session. In today's session, let us conclude our discussion. We've started our discussion by defining the registers. So we can say that are the combination of flip-flops and that have the capability to hold and to process some information and to hold some data. And counters are the special type of registers that works that have some predetermined set of states that maintains some count sequence that is dependent upon the logic implementation. And in this particular session, we have started our discussion by discussing a simple register. We have discussed the example of a simple 4-bit register that have the provision to have the clear or the reset input in order to clear those registers. And then we have discussed the example of the register with parallel load, and we've also discussed a 4-bit register in that particular case. And we've said that the value of this control line, the load line, that is basically responsible to load or unload the data, to load the data or to hold the data. So if we set the value of load equals to 1, then the data, whatsoever the data that is being applied to the input, that is being loaded to the output. And in 0 case, when we've set this value to 0, the outputs A0, A1, A2 and A3 should hold their previous value. And we've also discussed that if we have to provide the reset provision, we have to introduce a reset signal in all those flip-flops in order to reset that particular flip-flop. Till now students, I hope so you have got the basic concepts of the registers. Inshallah, we will meet in our second register session, in which we will be discussing the shift registers, and we will see what is the difference between the shift register and the normal register as well. And we will discuss the example of the serial addition operation implementing with the help of the shift registers. So go through your book, chapter number 6, read the respected pages, and if you've got any query, we can discuss those query in our discussion session. Till now students, Allah Hafiz.